So the modeling stuff kind of ends right here, like everything up above here, that's the modeling part. And then everything over here, this stuff is the calculus part. Does that make sense? All right. Let's take a look at another example here. I want to keep track of different models we have. So models. One we have is just a known volume. Let's just call it a geometric equation. Known geometric equation. Like volume of a sphere. Another type of situation that we were able to model is you had a right triangle and use the Pythagorean theorem. This is a very common model. These two are the two easiest, most common models. Okay. Let's take a look at another example. We might have a slightly different model here. A rocket is launched so it rises vertically. This vertically is going to be important. Vertically means going up and down. The camera is positioned so it is 5,000 feet from the launch pad. When the rocket is 1,000 feet above the launch pad, its velocity is 600 feet per second. Find the necessary rate of change of the camera's angle as a function of time so it stays focused on the rocket. We've had a lot of billionaires ship people or themselves into space recently. Maybe this example is very appropriate. I don't know if I'd want to fly into space. Would you want to fly into space given the option? Knowing that you might die? Any astronauts here? No feeling. Okay. This is the ground. This is the man or camera. Can I draw a camera? I can't. Put a C for the camera. Launch pad is somewhere over here. Launch pad. I don't like the location of my ground. Let me move my ground label. And then I'm going to have a sequence of dots representing the rocket. So the rocket starts at the bottom and it's going vertically, right? It's going vertically like that. That's the rocket. And if I drew lines connecting it, this is like the camera is pointed at the rocket. So we get a series of pictures that look like this. And there's some angle theta between. So here's one theta, here's another theta that's changing. Here's another theta that's changing. That angle gets bigger and bigger to keep track of the rocket, to keep the camera focused on the rocket. Does that make sense? Any questions? Okay. So now I want to draw a picture that represents this general situation. To me, it looks like we have another right triangle. Right, so here's the camera, here's the rocket, here's the launch pad. It's a right triangle again. Let's label the variables and let's label the constants. So it says the rocket is launched, so it rises vertically. I've captured that idea over here. The camera is positioned 5,000. So hard being lefty, you know. Some of you know how hard it is. Rocket's being launched vertically. It's 5,000 feet from the launch pad. So I didn't put that into my diagram. So here's 5,000 feet. You know, in my picture, I hope you could see that the 5,000 feet goes here. And you guys can tell that this is a constant, right? Like this distance isn't changing. So here's the $1 million question. Okay, seriously. Like here's the $1 million question. Do I want to put 1,000 right here? Right, because they say when the rocket is 1,000 feet above the launch pad, its velocity is 600 feet per second. Do I want to label this side as 1,000? Yes or no? I have one vote privately messaged in the chat box. What about the rest of you? Yes or no? Want to put 1,000 here or not? Okay. The answer is no. How do you know the answer is no? Two reasons. The first reason, we can see that this rocket is going vertically like this. That means that it's a variable. So I should give it a letter. Let me call it y. Okay. The second reason, they give me this velocity is 600 feet per second. They're giving me information that I'm going to need to use. So once I label this guy as my variable, then really they're telling us that dy dt is equal to 600 feet per second. Does that make sense? Is there any questions about that? So what are we looking for? Well, I still haven't finished labeling my diagram. There is one more variable that I want to label. Does anybody know what variable I want to label? This is also kind of important. So this idea, the fact that this is not a constant, that's a variable is very key. Like the number one way students mess this up is they put 1,000 there. But we also want to label any other remaining variables. We had one vote for Z. And Z would be the distance from the camera to the rocket. My question for you is, do you think we should label this as Z? I'm going to say no. And the reason why I'm going to say no is, number one, they did not give me dz dt. Number two, they're not asking me at what rate is the distance between the camera and the rocket increasing. That's not what they're asking me. What are they asking me? They're asking me to find the necessary rate of change of the camera's angle. Does that make sense? The camera's angle. So I do not want to label the Z. What do I want to label? I want to label the camera's angle. Does that make sense? They're asking me, what's d theta dt when vertical bar? What's the condition I want to put at the bottom right here? What condition do I want to write there? You're not sure. When you're not sure, you got to reread the whole question. A rocket is launched, so it rises vertically. Okay, I get that. Rocket's going up vertically. That's why this is a variable. A camera is positioned 5,000 feet from the launch pad. Okay, this side of the triangle is constant. It's 5,000. When the rocket is 1,000 feet above the launch pad, its velocity is 600 feet per second. So actually, they are actually telling me, let me move this over. They're telling me that this velocity is when y is equal to 1,000. And then they're saying, find the necessary rate of change of the camera's angle as the function of time so it stays focused on the rocket. So I feel like we should probably have 1,000 over here. Okay. So I am looking for actually the important piece of the important thing was actually to put the y equal to 1,000 for this guy. This part is less essential. The next thing I want to do is I want to relate the variables. So I have a right triangle here. I have a theta. I have two sides labeled. What's the relationship between theta, the opposite side, and the adjacent side? Does anybody know? Theta, opposite, adjacent. What's the relationship? SOHCAHTOA. Opposite over adjacent is the tangent. So when I relate the variables, these variables are related with tangent theta is equal to the opposite over the adjacent. Is there any questions? Okay, next you want to relate the rates. I'm going to use implicit differentiation. Chain rule, same thing, right? What's the derivative of the left-hand side here? Is secant squared theta your final answer? D theta dt. Remember, we're using the variable here. Maybe I need to write an extra step. We relate the rates by using implicit differentiation with respect to time, t. WRT means with respect to. So times d theta dt, right? So if I were to write an extra step, I'd write it like this. You got tangent theta is equal to y over 5,000. And then we're going to differentiate both sides with respect to time. Then on the left-hand side, you get secant squared theta times d theta dt. What about on the right-hand side? On the right-hand side, you don't need to use the quotient rule because this is just a constant. So we use the constant multiple rule. So that's like 1 over 5,000. That just stays there. The derivative of y is just dy dt. Okay. Does that make sense for everybody? Okay. Great. So now we're going to solve for d theta dt. You guys know that Secant squared is really 1 over cosine squared theta, d theta dt. That's 1 over 5,000 times dy dt, like this. And then I can multiply both sides by cosine of theta, and I get d theta dt is equal to cosine squared theta over 5,000 dy dt. And now what I want to do is I want to figure out when y is equal to 1,000. What that change in angle with respect to time is. Now we saw that dy dt was given to be 5,000 and was given to be 600. So I can write as times 600 over here. But what should I put? What should I put here? What's cosine squared theta? How do I figure that out? So we need to draw a little picture again. This guy was 5,000. This guy was 1,000. And here's theta. Anybody have any advice for me on what I need to do now? If I want to find the cosine. You guys know that cosine theta is equal to the adjacent over the hypotenuse, right? I have the adjacent side, that's 5,000, but I need the hypotenuse here. So we need to use the Pythagorean theorem again. So this is going to be 5,000 divided by the square root of 5,000 squared plus 1,000 squared. Does that make sense? Any questions? Okay. Cool. So let me write my answer like this. It's going to be 5,000 over square root of 5,000 squared plus 1,000 squared. You're going to have a 1 over 5,000. That's from this part right here. And they're going to have times 600. Okay. So I think you could simplify this out. You know, first of all, the 5,000 and the 5,000 cancel out. This guy becomes, I think it becomes 1,000 times rad 26. So when you work this out, you're going to get 3 over, oh, I need to square that, sorry. It's cosine squared. So when you work this out, you're going to get 3 over 26 radians per second. That's going to be our answer. Is there any questions about this this one? So we can step through this one more time. We know that the rocket is launched vertically. Camera is 5,000 feet away. We want to keep track of the angle. So we form a right triangle. This time we're not relating the 3 sides, we're relating the angle in 2 of the sides. Given information is the rate of change of the rocket. And the thing we're looking for is the rate of change of the angle. And this 5,000 is constant. And the 1,000 is not labeled here. This is a variable. I related the variables by using a trigonometric relationship. And then I related the rates by doing implicit differentiation. I differentiate both sides with respect to time. Got to use the chain rule. I solve for the rate that I'm looking for. And I realize that when I go to calculate the number, I have to do a little bit of extra work because I need to find the length of the missing side using the Pythagorean theorem. So let me label that in case. Pythagorean theorem. Okay. Once you have that, you can pop all the numbers in. And remember, our angles are always measured in radians. So this would be our final answer. Is there any questions about this? I made a slight boo-boo. I should not have canceled the 5,000 with the 5,000 because that was before I squared it. So you have to square the whole thing and then cancel after. So only one of those 5,000s cancel. So, okay. So if we look at our collection of models, we have a right triangle. But this time it's with trig relationships. In other words, it's that SOHCAHTOA stuff. Make sense? Any questions?